Okay, what is electricity? I'm not sure anybody knows, but um, we call it the flow of energy or current caused by a potential difference. There's some force that's causing current to flow. Um, and it has four main characteristics that we look at: the voltage, which is the force, the current, which is the amount of charge that's flowing, back in the coulombs. Uh, things can have resistance or opposition to that current flow because we only have zero resistance at like absolute zero temperature, because everything that's conductive, like your metals, copper, aluminum, silver, gold, all those will still have some resistance. And then power is the rate of doing work. Okay. So those are the four main things we're going to look at. But first, we'll start with the old atom. And an atom, there seems to be pretty good consensus that there's a nucleus with protons and neutrons in it. And it has an outer, what they call shell, at least in some of the models, where you have electrons that are negatively charged, and they're equal to the number of protons that's in the nucleus. So the net result is a neutral charge on the atom. When it becomes an ion, by getting an extra electron or losing an electron, then it becomes either a positive or negative charged ion. And the elementary charge, which I mentioned, which was at 6.25 10 to the 18th of a coulomb, is approximately what the charge is on an electron, how much it carries. So if you had that extra amount of charge come in to the atom to knock that electron out, okay, then it can go off and combine with another atom, either as an extra or filling a hole where there's one missing. That's how the charge actually gets transferred around. Okay, here's some of the old models. I mean, they first decided, well, atom was this little ball, and then it had positive and negative things in it. And then remember this back in the old days with the atomic energy thing. This is the one we most commonly use for these kind of discussions, where we talk about the electrons being in various shell layers. And this outer layer we call the valence layer. And that's the electrons farthest away from the nucleus have the weakest bond to the nucleus, to the proton. Remember, it's kind of like in magnetism, and even if you do the old comb trick, comb your hair and charge something up and rub a glass rod and charge, you get one positive, one negative. Electrostatic and magnetic poles repel and attract, same as here. Electrons are attracted by protons or vice versa, but the protons can't move. And two electrons will repel one another. So when you've got them in the shell, they kind of spread out because they're opposing one another, but they're both attracted to protons down here. So the ones out here are easier to knock out of its shell, orbit, whatever you want to call it. And that's what we'll call free electrons. I can't say much about this model, where I think this is just some cloud and they just wander in and out. And this is a lot easier to deal with where they're discrete layers or orbits.
Yeah, which looks like centrifugal versus gravitational force.
Yeah. Well, the other one was Schrodinger. He's famous for the cat in the box. If anybody's watched Big Bang Theory, they did that. Okay, so here we have a much simpler one, which they don't say what it is, but because it's got 3 electrons and can't really tell. If it was 3 and 3, it would be lithium. So we've got this outer one, which right now it's a neutral atom because they're balanced. If for some reason we get enough energy to knock that electron out of its orbit, okay, it becomes an ionized atom, and it would be a positive ion because it has one more proton than it does electron at that point. If it had captured an extra electron, it would be a negative ion.
It's got more electrons.
Right. And then sometimes they get in the crystal stuff where they're sharing electrons, and we won't talk about that much, except in semiconductors a little bit, part 2. Okay, so this is some of the official definitions of voltage, where they define it as the potential between 2 points of a conducting wire when a current of 1 amp dissipates 1 watt between those points. Now, we haven't talked about amperes or watts much, but these things are all interrelated, so it's kind of hard to talk about one without the other. Another definition is that the potential difference between those 2 points will impart a joule of energy per coulomb of charge. So what that is trying to say is this formula here, where a joule is equal to a watt second. In other words, how much work is done by 1 watt of power for 1 second. Now, hopefully this will be clearer later on. It's probably confusing right now.
Well, I haven't heard you used on anything outside of lightning.
Yeah, we won't do anything on the exams that I can recall with joules, but it's just part of the standard definition, and it is Joule's law. Everybody's got a law. Okay, here's a little animation showing a copper wire, and you have these electrons running around and going from one atom to another, and that's actually happens. They're not static, and how fast that happens is a function of temperature. I start heating that wire up, these become more and more active to the point where they become so active that they're generating photons, which means that that copper wire now is like a light bulb. It's giving off light. So there's a lot of activity. Now, if we apply a potential, like hook a battery up to that wire, okay, this, we'll talk about this a little bit, is actually showing electron flow. And you notice, if you're familiar with a 9-volt battery, this is the positive terminal where it's black. This is the negative terminal. So in some of this things, they talk about electron flow, particularly classes with the military when they're doing this stuff, as opposed to conventional current flow. And I'll talk about the 2 of them here in a little bit. But really, you need to think of this, instead of electrons, moving through here as charge. Because in fact, electrons only move a couple inches per second. There's no way an electron at near the speed of light goes around the circle, but the charge does. I might try to make one at some point, but in physics class, decades and decades ago, there was a demonstration where the professor took a long clear tube, filled it with ping pong balls. Okay. And if you tap one end of it, ping pong ball flies out the other end instantly. Ping pong ball didn't travel, fraction of an inch at most, but that force went all the way through, that energy, which is exactly how this works. It's the charge that's moving. So you've got electrons moving around, and it may jump from this one to this one, which leaves a hole, and back and forth. They don't necessarily migrate from one end to the other, but the charges, because it's being attracted by one potential and pushed by the other potential. Okay, so some of the common voltage sources you're going to see, particularly in amateur radio, are batteries with your handy talkie. If you get a technician license, mostly you'll be operating with a handy talkie. So you can get on the air for $30 with a Baofeng. The simplex or the repeater, a lot of repeaters around here you can get to. If you know CW with your technician license, you can operate in some of the HF bands. Probably nobody here knows CW, including me.
CW license back in the 70s.
Oh.
I can remember that.
I'm trying to learn it, but we'll see.
Yeah. I remember the SOS. That's about right.
Yeah. Well, CQ is the other one you need to learn. Actually, I started to get my license back in the 70s, and I couldn't do the code. I got interested in doing other things. And, we were launching rockets to the moon.
If you were to fly for an airline, you used to have a radio operator's license, and you'd have to learn Morse code.
I don't know if that's still true.
It's not.
Yeah. And they dropped it with amateur radio a number of years ago. Okay, so batteries are classified as non-rechargeable and rechargeable. Your typical flashlight batteries, carbon zinc, are not rechargeable, regardless of how you try, or the button cells in your watches and things like that. We have rechargeable. The most common is lead acid car battery. Everybody probably has one. Then they came out with nickel cadmium and nickel metal hydrides. Those are mostly replaced nowadays with different versions of lithium, lithium ion, lithium poly, lithium iron phosphate, all kinds. The other main source is your household power, okay, which we call 120 volts AC or RMS. And it's usually a 15 or 20 amp service. And sometimes you may have a 240 volt outlet if you've got big things, or if you get into amateur radio big time and want a 1500 watt power amplifier, you probably need a 240 volt circuit to plug it in. Okay, we measure it most of the time with a multimeter. There's things like line voltage monitors, which a lot of people may have. It's just a little meter that displays the AC line voltage. And then there's also laboratory instruments that are precision for measuring voltage, not that common. most of the multimeters will measure other things like AC and DC, current, resistance. Some cases, some of the newer ones will read capacitance. Most of them don't actually read true RMS. You can buy them, they cost more to actually do true RMS. And what that means is a cheap one, if you've got a perfect sine wave, will give you pretty close to the RMS value. If there's any distortion in that wave, or if it was a square wave or triangle wave, it's not going to come close. Whereas a true RMS, which uses a different technique, is going to be able to read that. Okay, so what did we learn? That free electrons, did I go too far? Okay. In metals is the mechanism that carries a charge from point to point. Right? They're jumping from atom to atom, and the charges are moving, but they don't necessarily go, the electrons don't necessarily go in the same direction the charge is being pulled or pushed, depending on your point of view. And an atom that gains or loses an electron is called an ion, either positive or negative. That voltage is the potential, or EMF, the force that causes the charge to move from point to point. And movement of the charge we call current. We measure it in volts, named after that Volta guy. He discovered a lot of other things. And most common are batteries and household power. Even with amateur radio, if it's not a portable or mobile base station stuff, will run on 13.8 volts. So you need a separate power supply that looks like a battery, basically. Okay, direct current. Old Benjamin Franklin is responsible for a lot of this stuff today. And at the time, they didn't really understand how this stuff works. So he decided that current flowed from positive potential to a negative potential. Well, that's stuck because it was there for years, and it's too hard to change after they discovered that electrons go in the opposite direction, charge goes in the opposite direction. So we call that conventional current flow, and we still use that most of the time. It's only when you get into semiconductors and vacuum tubes where you care about the charge or electron flow. Direct current always flows in one direction, from it's conventional positive to negative. If it's changing direction, we'll call it alternating current. And we'll get into that a little bit later. There's this thing showing conventional current going through the light bulb, and supposed electrons, which is really charge, going in the opposite direction. Okay, so direct current. Edison was big on DC, or direct current, and was trying to power the country with his dynamos all over the place, which were DC generators. Nikola Tesla, which you may have heard of, actually worked for Edison, but he was a pretty smart guy, really. He invented a lot of stuff. And one of the things, he was big on alternating current for power transmission. And he also got into trying to do wireless power transmission. He actually accomplished it, but it just wasn't practical. I mean, the I probably should dig up a picture of it. The setup he had, and I think he managed to transmit some power, maybe a mile, but it was just an enormous setup and just not practical. He left Edison and went to work for Westinghouse, who also was a proponent of alternating current, and they developed the AC generator and transformers for high voltage power transmission. So you're going to transmit power with a lot less current. So you're going to have less power loss because power is I squared R. So the lower the current, okay, the less loss you're going to have in the conductor. So if you raise it up to 1,000,000 volts, you've got a lot less current. And that's eventually what happened, and Edison lost that one. And we normally measure current. Again, most everybody in the field will have a multimeter. And like I said, it does a bunch of different things depending on how much you pay for it. And one of the more expensive ones you can get will actually do RMS. This is an example of a somewhat of a laboratory ammeter. You might use in breadboarding circuits and stuff to measure currents. When you use an ammeter, you put it in the circuit. Okay. Whereas when you're using a voltmeter, you're going to measure the voltage across the battery or across the load. To measure the current, you have to have it in the circuit to measure the current through. Okay, so conventional current goes from positive to negative, electron flow, negative to positive. Direct current always flows in one direction, positive to negative. We measure it in amperes, named after another scientist. And an ampere is equal to 1 coulomb per second. Remember, that's 6.25 10 to the 18th charges. Okay, so the other thing I guess that Edison or Franklin did was use the terms conductors and insulators. And conductor is normally a metal, usually has 1 to 3 valence electrons in its outer orbit. And the farther away they are from the nucleus, the easier they are to move, which is why silver, which has more protons than electrons, is the best conductor of all of them, because the valence electrons are easier to knock out or add to. This electronegativity thing is very confusing, but it's sort of it's the opposite of how easy it is to strip the electrons out. It's not my chart, so I'm not responsible for using that term, but I had to look it up. And I'm still not. It just seems odd. It's more in chemistry. Okay. Insulators have many more valence electrons in the outer orbit, so it's very hard to strip them out, which is where the high electronegativity means. And examples of that are mica, glass, your rubbers, plastics, those kinds of things. Exam question will talk about glass as an insulator. Conductors questions will be about silver, copper, and aluminum. We don't use gold. It is a very good conductor, not quite as good as copper, but it's expensive. But you use it where you need something like you gold plate connector fingers, things like that, so they don't tarnish or oxidize. Okay, the old periodic table. Here you can see copper, which is atomic number of 29, means there's 29 protons, 29 electrons. One in the valence orbit or shell. Silver, 47. And you can see that its valence shell is going to be much farther out from the center because, yeah, and this one doesn't, but it's got more shells, and I think it only has one or two valence electrons. Over here on this side are your look on mine, your helium and lithium, which is why lithium and sodium and those things are show up in some of your batteries. Over here in these green ones, you have gallium and indium and some of these things which are used to make semiconductors and substrates in semiconductors. And then, of course, you got oxygen over here, which has some very tightly bound electrons, so it's essentially an insulator by itself. Okay, so there's silver, and you see it's got one valence electron, and it's 1, 2, 3, 4, 5 in the sixth orbit out here. So it's easy to move this electron around. Copper has one also, but it's only got 4. So it's much closer. It's more tightly bound. So it's harder to get it to be free. Okay, so most metals are good conductors. Silver's the best, copper's next, most commonly used because it's cheaper than silver. Because it's got many free electrons. It allows current flow, and that's what we use for connections between electronic components. Insulators such as glass, plastic, rubber, mica is a really good one, which they use in some electronic components like capacitors or as insulators on transistors, things like that. It has very few free electrons. It prohibits current flow, and we use it for isolation or insulation. Okay, resistance. Okay, they define the ohm as the electrical resistance between 2 points of a conductor when a constant potential difference of 1 volt applied produces a current of 1 amp. So basically, they're using a lot of words to describe Ohm's law, where resistance is equal to the potential divided by the current. It was derived by actually experimentation, where Ohm sat down and he took different materials and applied different voltages across it, measured the current through it, and plotted it. And it turned out that it would essentially plot a straight line, your mx plus b curve. And he did it for a lot of different materials, and it was always a straight line, and it always had a slope. So that the slope of that line is what became resistance. Sometimes we use the Greek symbol omega to represent ohms, although most of the time you'll see it written out as ohms in honor of George Simon Ohm. Okay, so resistance is the opposition to current flow. And it's opposition to DC or AC current flow. It's the same. Now, when we talk about impedance and reactance, they're only affected by AC current. Okay, so resistance turns out to be equal to the volts divided by the amperes, and we measure it in ohms. Here's a plot of how similar to how he did it. And for each resistance value, which is the slope of these lines, and I've seen some pictures of his actual plots, and they varied along the line a little bit, but they were essentially a straight line. Okay, here's the pie chart, which I mentioned before, where the theory is if you can't remember the formula, just remember to draw a circle and write those three things in there. So if you want to solve for current, you divide E by R. If you want to find resistance, you divide E by I. And if you want to find E, you multiply I times R. So it makes it fairly easy to remember if you can remember to draw the circle. So if you have trouble with it, as soon as you get in the exam, when you start, turn your answer sheet over and draw your little circle, if you need it. Here's a picture of one of the first resistors. It's the size of a soup can. This is what modern day resistors look like, except it doesn't have any surface mount, which would be hard to see against these. They'd be like grains of sand along here. Oh, that was the other thing I forgot to mention on the electrons and atoms. That there was a thing I read to show you the scale. If you represented the nucleus of the atom as a grain of sand in the middle of the football field, the size of the atom would be the football field. There's a lot of space between them. Okay, to measure resistance, again, we're using the old multimeter on its ohm setting. For more accurate measurements, a lot of times we use what's called a Wheatstone bridge. And it's composed of two fixed resistors in this bridge configuration. There's a meter between them. This leg has a variable resistor, which you adjust with these knobs. And then you put the part you want to measure between these. And the theory is that when this one equals, these two are equal to each other. When you get this side that you're adjusting equal to this value, the voltage in here will be zero because it's a balanced bridge. So you've got the same voltage drop through both sides. And again, that was named after some guy named Wheatstone. Okay, so resistance, and that's like a test question, is the opposition to current flow. It's the ratio of volts to amps, where we get Ohm's law. We measure it in ohms. Sometimes we represent it with a mega. You use the little chart here to help remember it. Okay, so if I had a 12-volt battery supplying 2 amperes, what's the resistance of the load in ohms? Ooh. Now, these are like test questions.
I know. I'm brain dead.
It would be 6, right?
Huh? 6? Okay. if I got a 10 ohm resistor, it has 1.2 amps flowing through it. What's the voltage across?
12.
Okay. What's the difference between a conductor and an insulator? Well, you wouldn't pass that exam question.
If I go cut that cable over there and you hold on to the copper, you'll know what the conductor is. So the conductor allows the free flow of electrons, but the insulator does not.
Right. What's direct current?
It flows in one direction.
Okay.
From positive to negative, and the electron flow goes from negative.
Right. What's a free electron?
It is the electron that jumps away from the atom.
Right. The outer valence shell, easy to move.
Which is light.
Which is lightning. Actually, lightning is alternating current.
The flash we see is actually the negative charge, isn't it?
It's like I think it's like 3 cycles.
Yeah.
Yeah. And what you see is ionized air. So you've taken electrons away and heated the stuff up to where you got a plasma, you got photons coming out and stuff. And it's actually charge going from the ground up.
That's why I see joules. That's where.
And the most common source of a constant DC voltage. Battery. Okay. Electric fields. Okay, if you have potential differences, you have electric fields. Now, this one isn't the best chart, but it was the best one I found at the time. So if you think of these little circles here as conductors that you're looking head on. What?
Restroom break.
Oh, you need a break? Well, fine. Just, sure.
Sure with me.
Okay, it's coffee time anyway.
Motorola, and you do radiation power on cover center.
You got this speedy electric.
Okay. Let's start to look like that.
THC gummies.
Okay. No profanity now. Okay, so if we have electric potential, we have these electrostatic fields, and just like magnetic fields, they oppose and attract. So I think in this one, it's trying to show, if you looked at these as wires and you were looking end on, and you have current going in one, current coming out the other, it's just showing the direction of that field around that wire. Now, as these get closer together, you see where there's, let's assume the blue ones are negative, are current going in. The fields are opposing one another. This is the same thing, but in the opposite direction. And here they're opposite polarities, so those fields are attracting one another. Now, if you've ever seen a it's terrible when you get old, you can't remember things. They have a little jar, and I can't remember the name of it, but it's got a rod down the center of the stopper, and there's 2 gold leaves attached to it. So if you charge that up, like with the comb, and it puts a positive charge. If that's the right one. The gold leafs will actually separate because they're light enough and there's enough force there. It will actually cause them to separate. If you can get opposite charges on them, they will collapse back together. You can actually see that with wires. In fact, what was it? There was something here yesterday or today mentioned somebody shorting a power cable, and it actually drew enough current. The force was able to, it was like zip cord. It was actually able to separate that cord, repelling the thing together.
Because you meant electrons because they're opposed.
Well, it was a short to the two wires, and they just ripped it apart. There's some big forces.
A lightning jar or something.
Leyden jar. That's what I was trying to remember. Yeah. They do a lot of physics demonstrations with those things. Okay, so these other ones are showing like a wire along adjacent to a plate of some sort and how those fields are. If we had two plates, okay, with opposite charges, then you've got pretty much a constant field between them, where this is how a capacitor works. In this one, what you've got, assume this is a wire and you're looking end on, and centered in this conductive tube, which is how coaxial cables work. Somebody got the bright idea, instead of having two wires side by side, where if you don't, like we talked about, twist them to reduce the interference, they're susceptible to outside interference because you've got the other fields can affect it. That if you took one of those and
Wrapped it in an insulator.
made it into a sheet and wrapped it around, okay, you'd contain the electric field within it. Okay, so it's not affected by any field from the outside, either magnetic or electrostatic. And that's how a coaxial cable was developed. So regardless of the whether you got it polarity one way or the other, okay, you've got this field contained within there. So if we have these plates that are separated by a certain distance, okay, with a potential across them, you're going to get a uniform field. And this is what turns out to be what we call a capacitor. So you've got a charge building up on one plate, an opposite charge on the other. So you have this field between them. The strength of the field is going to be determined by the distance between them and the area or surface area of these plates. So we wind up calling that a capacitor because it can actually store energy in that electric field. And how much it stores, and we call the fact that it can store that energy, we call that capacitance. We measure it in farads, named after Michael Faraday. Everything is named after somebody. And they decided that a 1 farad capacitor can store 1 coulomb, that's all those charges, at 1 volt potential. So, and the amp represents the flow of 1 coulomb per second. So a 1 farad capacitor can hold an amp second of charge at 1 volt, which is how we come up with the charge is equal to the capacitance times the voltage. And in this little picture, we're showing the dielectric in the center, which is another word for insulator, with the 2 plates and the charge on the actual physical formula for calculating capacitance based on the area and the separation of the plates I don't have on here, and that's not part of the test. But it's a fairly simple formula, and you can easily figure out what the capacitance would be if you took 2 pieces of aluminum foil and separated them with a piece of wax paper, and you got a capacitor. One of the early ones, actually, it wasn't Leyden. It's something else.
You got it right.
I don't remember what it's, still don't remember what it's called. But anyway, the Leyden jar is one of the early capacitors. Now, it says that they filled these with water. I'm not sure I understand why, unless it's to make a better connection. But essentially, the capacitor is the foil or the conductor on the inside of this bottle versus the outside. So you have a connection to the in one and one to the outside, and you've got a crude capacitor. Most of the modern ones were made, the earlier ones, with aluminum foil and a paper, like a wax paper separator, and they rolled it up into a tube. And they call those tubular paper capacitors. And they're still around. Like I said, the Leyden jar was one of the first ones. And old Frank Benjamin actually invented one he called the Franklin square, which was 2 square plates of glass separated by, 2 plates separated by a square piece of glass. This is a picture of an assortment of more modern capacitors. These are electrolytics, which process is slightly different because they use an electrolyte to help migrate the charge. So they can actually hold more per volume than the basic electric field type. These are ceramic capacitors, which are 2 metal plates separated by a piece of ceramic. These are what we call air variables, which you use for tuning, basically, having an adjustable capacitor. And it's still 2 plates separated by air. One of them moves, so the plates can mesh together, and how much they overlap determines the amount of capacitance.
And they'll still hold a substantial charge even if disconnected from a power source.
Yeah, if you had one in a transmitter or a matching network for a high power amplifier, and you got a few thousand volts across that capacitor, it's got a little charge.
The old cameras, that's how the flash cubes went off. The flash cubes were powered by a capacitor.
Yeah.
That was my first failed experiment.
Yeah, back in machinery lab in college, we had this big board with all kinds of switches big knife switches and stuff to run the great big motors and things. And we'd take electrolytic capacitors and hook them up to the board and turn the power on, blow up. It was interesting. They make a lot of fluff. This is a typical ceramic capacitor where it's got a thin piece of ceramic and they plate some sort of metal on there and make the contacts. and then coat it with usually another kind of ceramic to insulate it. It's probably the most common capacitor you'll see. They have it covers all the smaller values, and they're cheap. Obviously, it doesn't take much to make them. This is a kind of a cross section of a tantalum electrolytic capacitor. So you've got, I'm not sure how well you see, but this outer, what they call centered tantalum, and an inner, and this centered means it's made up of like ground tantalum that's sort of pressed together. So there's holes in it. It's porous. And then there's an electrolyte in there, and it is what actually carries the charge between the two. But that's typical to an electrolytic capacitor, not necessarily all tantalum. That's more modern. Okay, here's a typical circuit. I'm going to show how we charge and discharge a capacitor. I've got a 10 hertz square wave coming in through this resistor just to limit the current a little bit, and a 1 microfarad capacitor. So when we simulate that, the blue line is our square wave, which is going from 0 to 10 volts. And if you see, the yellow line is the voltage across the capacitor. So it starts at 0 and it slowly charges up. And how fast that charges is a function of the current going in, which we limited with that resistor. Because if I had no resistor there, it would almost exactly follow the square wave and you wouldn't be able to see the effect. Now, once it's charged up, we take the voltage away and it slowly discharges back through the circuit, through that resistor. And this plot is the actual current flow. So you see it instantly goes up to 1 milliamp, which is as much current as we're going to get through that 10K resistor. If I had a 1K resistor, it would be 10 milliamps. And it slowly decreases as the voltage charges. So once it's charged, there's no more voltage or current flow into that capacitor. And that's capacitor at DC can actually act as an insulator or block DC voltage, which you use a lot of times in circuits. Okay, so capacitance, test question, is the ability to store energy in an electric field measured in farads, constructed from conductive plates separated by an insulator. Another test question. Current decreases as the capacitor charges up to the applied voltage. And we talk about the current leads the voltage. Okay. The current goes up instantly. The voltage goes up slowly. Okay. And there's a little memorization thing called Eli the Iceman, where for an inductor, which we'll talk about in a minute, E, the voltage leads the current. For a capacitor, the C, the current leads the voltage. So that's supposed to be able to help you remember the two of which one has leading voltage, which one has leading current, or vice versa. Okay, now magnetic fields are also created when you have a current flowing through the conductor. So you not only have an electrostatic field or an E field, but you have an H field or a magnetic field, similar to magnets. Okay, you've got that magnetic field, and opposites attract, and the same polarity repels. So in this one, we're showing conductor with the current going in that direction, and use the right-hand rule. Okay, your thumb is the direction of the current. Your fingers are the direction of the magnetic lines of force. So, and that's kind of an arbitrary, somebody decided at some point in time. So they're circulating in the counterclockwise direction if you were looking down from it. You have the opposite current over here, so they're going in the opposite direction. Now, when we take that wire and we wind it into a coil, okay, the magnetic lines of force tend to concentrate in that common area between them. Okay, so this is how we build what we call an inductor. Now, a wire by itself has some inductance, but basically you need many turns to get a lot of inductance. And to get even more, you put a material in the core that has what we call permeability, and it can concentrate the magnetic lines of force. In other words, it acts like a magnetic conductor. So it's things like iron or the ferrites and things like that, which have very low magnetic resistance. So this is just showing, again, with the current going through the coil, okay, the concentrated magnetic lines of force. You get a little bit on the outside, but most of it is in the center. This is sort of redundant, but we call this inductance the ability to store energy in the magnetic field, whereas capacitance is storing energy in the electric. So it works the same on the opposite. And this is a typical solenoid type inductor where you've got some sort of magnetic. Usually on these, it's like a ferrite rod. There's another picture of an actual one. This is a toroidal inductor where it's ferrite or powdered iron material in the shape of a donut. Now, the reason they've gone to these is there's virtually no magnetic lines of force outside of that donut. Everything's concentrated in the center. And it makes a nice compact inductor. There's some other forms here where they're wound terms around this little insulated thing. These are surface mount inductors where there's a coil inside of that. These are not to scale. This thing would be maybe 1/8 of an inch square. This is a small inline inductor. Sometimes we call them chokes. It looks like a resistor, but there's actually a little coil in there. This is just another form. Okay, so we'll do the same thing with the inductor. Apply our square wave through a resistor and a 10 millihenry inductor. I picked those so it makes a nice chart. So here we're applying the square wave, and you notice the voltage on the inductor follows that square wave immediately. Okay, and then the voltage decreases to 0. When we take the voltage away, okay, we get an instant polarity change because the magnetic field is where the energy stored is collapsing. So it's trying to prevent itself from collapsing, so it creates a current in the opposite direction. So we see that field in the opposite direction, current collapsing. If we look at the voltage, okay, we see the voltage going from 0 up to, excuse me, not the voltage, the current starting at 0 and going up to the maximum value where the inductor has as much charge in it as it can hold. And at that point, from the DC point, it looks like a short circuit. I mean, it has some very small resistance value, but it's essentially a wire. And that's why you're going to see different behavior with alternating current because you're hitting this. So it looks like initially it looks like an open circuit to an AC waveform. So depending on the frequency, and this is the higher the frequency, the more impedance the inductor has. Whereas the capacitor is just the opposite. The higher the frequency, the less reactance or impedance it has.
So the inductor basically works as an inverse to the capacitor.
Yes. And that's how we get resonance coming up shortly. So the inductance is the ability to store energy in the magnetic field measured in henries. We make inductors from coils of conductive wire. The current increases as the magnetic field increases, and the voltage leads the current, the old Eli the Iceman. That question is not on the technician test. It does come up general or extra. Okay, so circuits. We kind of have two. We have analog and digital. We'll talk about digital in part 2. In analog circuits, they're made up of series and parallel combinations of active and passive components connected together with conductors. Your passive components are resistors, capacitors, and inductors. Your active components will be things like tubes, transistors, diodes. I guess you'd even consider things like relays, transformers, although transformer would be passive. Okay, so we start with a series circuit. In a series circuit, like series, all the components are connected together in series. So there's one path through all the components. In this one, we're showing two resistors. We got a 100 ohm and 1,000 ohm resistor. We have an ammeter in the circuit. Remember, it has to be in the circuit to measure current. So we're measuring the current at this point. In this one, we're measuring a current between the two. And in this one, we're measuring the current down here, and it's always the same. Because the current through the series circuit is going to be the same through all the components. It doesn't matter where you measure it, you're going to get the same current measure. If it's a parallel circuit, in other words, there's more than one path. Okay. The one thing that's common is the voltage across each of these legs is going to be the same. The current, however, is going to split. So the current at this point, we'll say I, okay, splits off as I1 through resistor R1 and as I2 through resistor R2 and R3, which are series. So we actually have a series and parallel combination circuit. But the voltage across this resistor is going to be equal to voltage across the battery. the voltage across these two resistors is going to be the same as the voltage across the battery or the voltage across this resistor. Any questions? You're staring.
Yeah, I was thinking about it in my head.
Just feel free to ask. Okay, so
So the voltage is gonna be the same across the path.
that's the key. The
Current's gonna be
voltage, right? On a parallel circuit, the voltage will be the same. On a series circuit, the current will be the same. Okay, so if we have resistors in series, because they're easier to deal with, then we just add them up. Okay, so the total resistance is going to be equal in this circuit to R1 plus R2 plus R3. And if I put substitute values, okay, 1K plus 2K plus 3K is 6K. Just simple arithmetic. If I put them in parallel, however, here comes the old reciprocal. So if I have those three resistors in parallel, I have to take the reciprocal of the sum of the reciprocals. So if I substitute, I get 1 over 1K, 1 over 2K, 1 over 3K, which would wind up being 1 over 6K, which if you do it on your calculator or your head, comes out 540 5.45 ohms. And again, you notice the value is less than the smallest value of the combination. It's always going to be smaller. If it was if one of them was infinite, it would be equal. So it's always going to be smaller. So on the exam, that's one way to make sure you got the right answer if it's at least smaller than any of the ones in the circuit. Okay, capacitors in series. Now they behave like resistors in parallel. It's the old reciprocal of reciprocals. So you just go through the same exercise, and once again, the resultant value is going to be less than whatever the smallest one was. Now, sometimes on a test, they'll give you maybe two. Well, yeah, they'll give you two in series, two capacitors in series with the same value. Now there, you don't have to go through all that. Okay. You just multiply them and divide by the sum, and you come out with basically half. So if that was 6 microfarads and 6 microfarads, the result would be 3 microfarads. Or you could do the reciprocals. But if it's more than, that only works when there's 2, to multiply and divide by the sum. So capacitors in parallel act like resistors in series. You just add them. Okay. Inductors in series act like resistors in series, because each one opposes the flow. So the more of them in series, the more opposition to flow. If they're in parallel, okay, and it's like capacitors in series or resistors in parallel. And you do your little reciprocal formula. Okay, so in a series circuit or in series, resistors and inductors add up, capacitors are reciprocals. Current is the same through all the components in a series circuit. In a parallel circuit, resistors and inductors combine as the reciprocals. Capacitors add, and the voltage is the same across all the components. Okay. There was this guy, Gustav, Kirchhoff, who came up with another set of laws. All these guys like laws. And they're used to analyze circuits. You don't really need it for a simple series or very simple parallel circuit, but when they're more complex is where these things come into value. And his voltage law was that if you go around the loop in a circuit, the voltages will all add up to zero. Okay, because in our let me back up. Well, we can use this one. I have a voltage on the battery at this point that's positive to negative. Okay, if I go around this loop, okay, I have a voltage across this. Let's pretend this is a resistor, so we don't have to worry about it changing its value. I have a voltage across this resistor in this direction that's equal to this. So if I go in this direction, I've got a positive voltage and then an opposing voltage. The sum is zero, because I'm going to take this one minus that one. Likewise, if I went around this loop, okay, I've got a voltage this way and a voltage this way. So I'm going with this voltage against this voltage. They add up to zero. Does that make sense? Now, his current law says that the currents flowing into a node connection point must add up to zero. So, I forgot I had this one. Here's the voltage law again. Okay, so we can see that we have E here and V1 across R1. So if we go in that direction, okay, we've got opposing voltages, so there'll be zero. Same thing over here. And this was also showing that the current through these two resistors is going to be the same because they're in series. Now, over here, we have the current law. So we have a node at this point. So I have a current I going into this node, and I have a current I1 coming out and I2 coming out. So those will equal this one. So it's zero. So when you get into trying to analyze circuits, those are very important concepts. Not that you need to know that for the technician exam. Okay, so the voltages around the loop add up to zero. Parallel elements have equal voltages. I should have put in there, series elements will have equal currents, and the currents in and out of a node add up to zero. Need to fix that chart. Okay, power. It's the rate of doing work. We measure it in watts. And work is the amount of energy used in joules. So 1 joule, we said, was equal to a watt second. And this shows how we get all that stuff to the power formula, where power is equal to the voltage times the current. Or if you play substitution with Ohm's law, it's equal to the current squared times the resistance. Or it's equal to the voltage squared divided by the resistance. So they're all things you can derive between the power equation and Ohm's law equation by substitution. So some examples of power calculations. If I got 12 volts at 1 amp, it's 12 watts. If I had 50 watts at 10 volts, there's 5 amps of current. If I had 100 watts at 1 amp, it's 100 volts because I'm dividing power by current. If I have, if I want watts and I know current and I know resistance, I square the current. So it's 2 amps squared times 50 or 200 watts. Likewise, if I want watts and I know voltage, I square the voltage divided by the resistance and come out with 100 watts. This one is some significance because most amateur transceivers, base stations, will put out 100 watts. So into 50 ohms. So that means it's putting out 70.716 volts into that 50 ohm coax. And that's RMS volts. Again, we have, we want to solve for volts. So we take the square root of the watts times the resistance. And if we wanted to do amps, then we knew power and resistance, we take the square root. Remember, an exponent to the minus 1/2 is the square root.
So if we took like a simple light bulb on let's a single circuit, so you have a 100-watt light bulb.
Right.
So 100-watt light bulb, 120 volts, you draw 0.83 amps current.
Right. Okay, here's a bigger pie chart, which I don't have copies of, but you could find it on the internet, which relates all of these things together, all the different laws. So if you want voltage, okay, if you know any of these are the equations. If you want resistance, there's 3, depending on whether you know current and voltage, current and power, voltage and power. Same thing for wanting power. So these are all derived from those first 2 equations, the power law and Ohm's law. And I don't remember all those off the top of my head. If I have to, I just derive it again. Because I do remember Ohm's law and the power law. As you get older, you might forget too.